We have defined some of the main parameters of a wireless system that are related to the antenna, the wave impedance on one side for the wave, and for the antenna we also have the antenna impedance, the gain, the effective area. Now we're going to go to the practical situation where we have a transmitter and a receiver. They are both connected to antennas that are separated distance r. And we want to establish a balance of power. In other words, we want to know how much power we receive here when we put a certain amount of power here on the transmitter. There are communication systems that are one way, in the sense that we have a transmitter and a receiver. For instance, this is the TV set at your home. There's a broadcaster and you are the receiver. But there are other situations which are different. For instance, when you use a mobile phone, you just transmit, you go in this direction, but you also receive. So here, your mobile phone is doing both functions. It's just sending and receiving information. Both are similar, so we are just going to stick to one of those ways. We have the transmitter with two main parameters. The first one is the power that this transmitter could deliver. This is what we call the transmitted power. And to simplify things, we don't take into account cables or other interconnecting elements here. So for us, the transmitted power is just the power accepted by the transmitting antenna. Maybe the transmitter is delivering more power, we have cable losses, other element mismatches there, so we just stick to the power that is being radiated here. The antenna will send this power to the space with a certain gain, and we call this GT. This is the gain of the transmitting antenna. At a certain distance r, here, we have the receiving antenna. This antenna is going to see the wave coming towards it and is going to extract power from this wave and send it to the receiver. So here we have, from the point of view of the wave, two things. One is the electric and the magnetic field that is arriving to the antenna, and this is the power density that is transported by this wave. So those are the parameters related to the wave. And now we have the antenna, the receiving antenna. In the receiving antenna we may have different parameters that are related, but here you have the main ones. The effective area, the effective length, and the gain of the receiver antenna. That gain will be the gain of this antenna when it's radiating, which is related to the effective area of the antenna. So here you have the parameters and how they are defined. This is the receiving antenna, effective area, length, and gain. And we have here the power flux density and the electric field with this unit. And what we want to know is just the power received by this antenna. And this is a very important balance, because this is going to tell you the ratio of the received power to the transmitted power. And this is what we call a link budget. It's just a list of parameters where you start with the transmitter power and you end with the receiver power. And this is how it's going to evolve our calculations. We're going to start on this line here, and we're going to follow this line across. And you see brackets here that are going to define terms that are related to it. And at the end, we are going to look for the power balance, which is also called Friis transmission equation. It's named to honor Harald Friis, who was the Bell Lab engineer who developed this budget. So we start on the receiving end. I want to find the received power, this antenna. This is what we want to see. The value of this power is just the product of two things. the power density that is arriving to the antenna and the effective area of the antenna. So this is what you have here. So the received power is the power flash density times the effective area of the antenna. So now let's go to this line below and write the power flash density. And this is related to the transmitting antenna. We have the other antenna here. So now we want to see how much power density this antenna is producing on the receiving antenna. And the first thing we have to do is to take the radiated power, which is PT, and we divide it by the spherical surface at that distance, 4 pi r squared. And this will give us the power flash density if the antenna were isotropic. And this is just the value. The first thing you have to know is that this power density decays like the square of the distance, because we are spreading the power on a larger and larger surface as we go away from the antenna. But since the antenna is not isotropic, then we have to multiply this by the gain of the antenna, and this is the product we have. So the power plus density is just the product of the power of the antenna, the gain of the antenna, divided by 4 pi r squared. If you are interested in knowing also the electric field, then the electric field square divided by the wave impedance, and you have here the parameter that is related to the permeability and the permittivity of free space, or the vacuum, for most of the purposes, which has a value of 120 pi, or 377 ohms. This wave impedance, you put this value here, the square of the field here. So this will give you the value of the electric field that is arriving on the antenna. We are not going to use this in this calculation, but it's interesting to know. We are going to continue with this term. And now we write this term up here. So we have that the power flash density arriving on the receiving antenna, the one that is here, is the product of the power transmitted by the antenna and the gain of the transmitting antenna divided by 4 pi r squared times the effective area. If you look at this product, it's an interesting one because you can have the same value of power flash density with different values of transmitted power and gain. So this product of those two terms, we call this the equivalent isotropically radiated power. That's an important parameter, and it's normally described by this acronym EIRP. Tells you that you can have the same value if you just trade gain and transmitted power. So you have a system with a certain power and a gain. You could have the same effect on the receiving antenna, for instance, if you double the power and you decrease to 1/2 the gain, or you go the opposite way. In some cases, it will be simple to increase the power. Your transistors could deliver more power, and you don't have to change the antenna. In other cases, for instance, on board a satellite, you are limited by the power you can radiate. So if you want to increase this value, you have to increase the gain of the antenna. You need a larger antenna, but maybe you can do this. That depends on the system. It's simple to do, or it's very hard to do. For instance, in a mobile phone, you are limited by the size of the phone, and you don't want to have large antennas going out of the mobile. So here you have to play with both parameters. But it's a very important one. And we have the effective area of the receiving antenna. But you can also write this effective area in terms of the gain of the receiving antenna. And remember, this was equal to lambda squared divided by 4 pi and the gain. So here now you have the transmitted power, the gain of the transmitting antenna, the gain of the receiving antenna, and then lambda divided by 4 pi r squared. And this term is also interesting to know because you are going to be seeing it frequently in this session. It's called the free space path law, or the path law, or the propagation law. And look at this number. this number is dependent on the distance. If you increase the distance, this becomes smaller and smaller. We write this with this convention. It's a very symmetrical term. So now, if we want to establish a balance, what we have to do is just divide this received power by this transmitted power. Okay? And this is the transmission equation. And look, it's the product of the gain of the transmitting antenna, the gain of the receiving antenna, and the free space path loss. Normally, this is value that may take a range which is quite high, depending on the size of the antenna, but here the dominant term is this one. Since you try to establish a communication link to a long distance, then that means that this term could become quite small. And you have to overcome this space propagation penalty, which is just the main parameter limiting wireless communication systems. We frequently use the decibel as a unit or as a tool to express power ratios. The unit is a bell, which is just log 10 of a ratio, but we normally, since this is a very coarse unit, we just use the decibels. This is exactly the same thing we do with metric. We could use meter, kilometer, but sometimes in a rule you will see that we use centimeters or millimeters. That depends on what we want to see. In power, it's normally interesting to use the decibel, 1/10 of a bell. The name comes also from Bell. He was the inventor of the telephone. This is just the log scale, and logarithm scales are interesting because they do two things. When numbers are very large and you take the log, this becomes small. It compresses long numbers. But it does the opposite with the small values. If something is between 0 and 1, a log scale will expand it. This is the way to define the decibel. You have the ratio of two powers, somewhere in the circuit or in whatever you want. It's always the ratio of two powers or two power densities. You take the decimal log, and then you multiply, this is the bell number, you multiply by 10, then you get the decibels. And we represent by dB. And we normally say a dB of power ratio. If we use here a reference power, then we put something afterwards the dB. For instance, you will see frequently dB watts, or more frequently even dBm. The dB watt is just the power expressed in this log scale when you take a reference of 1 watt. A milliwatt is when you take a reference there, and we call this a dBm. We don't put here the double. You just dBm. And this is probably the most frequently used in communication systems and the receivers. If we use power densities, that will be watts per square meter or milliwatts per square meter. And you could use other different ones. Since this is a 10 log, if you know the number in dB watts, if you add 30 dBs, then you get the number in dBms. Because there is just a ratio of 1,000 in power. But we also use from time to time dBs on electric, magnetic voltage or currents. Why? Well, you all know that the power, for instance, in a circuit is related to the square of the current or to the square of the voltage. If you write the power in terms of voltages or currents, that will be the ratio of currents square. And in a log, this is the same thing that taking the ratio and multiply by twice 10, that means 20. So when you deal with fields or voltages or currents, you should use 20 log of this ratio. And here we have new units to talk about. We use talk about dB volts when the reference is 1 volt, or this is a very frequently used one in broadcasting, dB microvolts, or if you are talking about fields, dB microvolts per meter. And this is the reference. In one case is 1 microvolt or 1 microvolt per meter. And once again, you can transform values from one to the other. For instance, if you know the voltage in dB volts and you want to refer it to dB millivolts, you have to add 60 dBs. The ratio here is 1000, but since this is a square, it's 1 million, and that's why you have here 60. Or if you want to write it in dBs per microvolt, then you have to add 120. So those are just the rules to use decibels. We're going to use this along this session and the cases we're going to study later on quite frequently. Now, if we apply this to our link budget, then you have to remember this. We transform multiplications. Here you have the product of 2 power divided by another 1. The units will be power. We take the 10 log and we transform multiplication and divisions in addition and subtraction. When we write the link budget, remember that was the product of gain of the transmitting and the receiving antenna times the inverse of the loss, or the propagation loss. So in dBs, this is a simple expression. It's just the sum of the gain of the transmitting antenna, the gain of the receiving antenna, and then we subtract the losses. This first term is the propagation loss in free space, and we have to add any other losses that will be present in the system. And this is how the free space propagation loss looks like. It's 20 log of 4 pi r divided by lambda, and you can write this as a fixed number, and 20 log of the ratio of the distance in terms of wavelengths. That means that if you keep increasing the distance, then the loss will just go as 20 log of this value. But also you have another expression, which is simple, which is once again 32.5 plus 20 log of the frequency in megahertz and 20 log the distance in kilometers. That means that any time that you multiply by 10 the distance, then you get 20 dBs more to be added on this loss. So those are the limiting factors. Those help you. They are positive in the sense that they raise the received power, and these two others, just as good losses could do, just decrease this value.